Here's a rigid body kinematics problem, which we're going to approach without using Euler's formulas. Instead, we're going to do it with the idea of the center, the instantaneous center of rotation. And we're going to apply that in order to find the angular velocity and the angular acceleration of a link, right? And if you'd like to see anything similar in the future, or if you have any suggestions for any topics or specific problems related to maths, physics, or engineering, please let me know in the comments. So let's read the question first. We're dealing with a hydraulic cylinder C, which is imparting the end A of this AB link a constant velocity v0 in the negative x direction. So one thing we could write, if we write this in vector form, is that the velocity of A as a vector is equal to minus v0 times I, right? And the question already tells us, well, the question already gives us a suggestion for the directions of the xy axis, right? So it tells us that x is to the right and y is upward, so we're just going to use that. Now, we won't really use vector notation here because we're not using Euler's formulas. Instead, I will redraw this figure as a sketch, and it will be obvious that it's actually a triangle at the end of the day. So I will draw it like this, and then I'll make this a bit thinner, and then there's this side of the triangle, and of course this angle here is 90 degrees, right? So this length is L, and that's the length of the link, which is assumed which is a constant. It doesn't change with respect to time or anything. And this is X, which does change because this point A here keeps moving to the left all the time, so X is getting smaller and smaller as time goes by. And then let's call this B, and this is going to be A, and let's call this point maybe O, right? That's the origin of the coordinate axis. Okay, so what we can then do is we can try to find what the center of the instantaneous center of rotation is. And we do that by finding out the directions of two velocities on link AB. Okay? So we know, first of all, what the velocity of A is, and we know the direction of that, and we know that it is actually to the left. And we also know the direction of, or we can deduce the direction of the velocity of B. So if A is going to the left, it means that link AB will rotate clockwise, which means that B is going to move upwards like this. Okay, so we can find the location of the center of rotation by just drawing perpendiculars to the two velocities. So one is going to be like this, one is going to be like this, and we're going to end up with this point here, which I'll call it C. The C is the hydraulic cylinder, but we don't really use that. So we're going to call this point C. Now, what this means, again, as a reminder, is that while this is the instantaneous center of rotation of link AB, it means that every single point on this link is, for a moment, rotating about C with the same angular velocity omega, which we don't really know yet, but we can find. So let's see how we can do this. Now, this, as we specified earlier, this is a right triangle, which means that this side we can find using Pythagoras, and that's going to be the square root of L squared minus X squared, like that. So let's try to write down what the velocity of A is based on the angular velocity. So we have that the velocity of, or the linear velocity of A is equal to the angular velocity of AB multiplied by the radius, right? And so that's the distance to the center of rotation, which is what we just found as square root of L squared minus X squared. Okay. So let's find out omega, which is therefore VA, divided by the square root of L squared minus X squared. Now, we know what the velocity of A is, and that is going to be V0. That's what the question tells us, over L squared minus X squared. Okay, now, once again, I will not actually leave this value of angular velocity as it is, because we will have to take the direction of rotation into account, right? We know that AB will rotate clockwise, and if we used Euler equations, then we wouldn't have to take this step, because Euler's equations will do that for us instead. So I will say that omega is minus V0 over square root of L squared minus X squared. Okay, and now the minus tells us that link AB rotates clockwise. And that's the expression for omega. So I think we solved half of the question, right? So we also have to find the angular acceleration now. So to find the angular acceleration, all we have to do is just differentiate omega with respect to time. So in this expression for omega, we just have one variable because everything else is constant. V0 is constant, that's what the question tells us. L is constant because that's the length of the link, which is constant. So it's only x that depends on time, right? Because x is always getting shorter. So if we differentiate this, this is what we will have. I'll keep v0 where it is, and this will be L squared minus X squared. So I differentiated that as 1 over the function. And now we use the chain rule to differentiate the square root, which is 1 over 2 square root of L squared minus X squared. And now we use the chain rule again to differentiate what's inside the square root, which is 0, because L squared is a constant, minus, and then we have X squared, which is a power, so that's 2x. And finally, we differentiate x itself, which is x dot. Okay, so it's a pretty long expression, but as you'll see, we can simplify it a bit. So first of all, we can cancel out the 2's. So what we'll get is an expression for alpha, for the angular acceleration, which is the following. So this will be minus v0x, and then we have x dot, and then this is divided by, I can write it like this actually, L squared minus X squared to the power 3 over 2. Okay? Because this is to the power 1, this is to the power 1 half, so you add the powers and you get 3 over 2. Now, we know everything in here except for x dot. We don't yet have an expression for x dot, but we don't have to worry about that because we know what it is. So x dot is actually the rate of change of x, which is v0, or rather it's minus v0, like this. Okay, because x changes, x becomes smaller, so we have to take this into account. So finally, from those two, we get our final expression for alpha, which is v naught squared times x divided by L squared minus X squared to the power 3 over 2. Of course, there's no minus anymore because this minus and this minus canceled out. So it tells us that the angular acceleration is positive, meaning that it is counterclockwise. So on the drawing here, here's what we have. We have that omega is clockwise and alpha is counterclockwise, which means that while the link is rotating clockwise with an angular velocity omega, it's actually slowing down because the angular acceleration vector is opposite to that. So yeah, that's the final expression for alpha. That's what omega is, and that's the end of the question.